Hello there, welcome back to our channel. And what we see on the screen is a BJT circuit configured as a common emitter amplifier. So we have seen this circuit, it's a DC operating point analysis. We've seen the transient response, we've seen the AC response as well. And this time I have brought to you this circuit again to explain how to compute or calculate an input resistance, or more familiarly called as input impedance of this circuit, right? So R in. So in our previous module, we theoretically analyzed the small signal equivalent circuit of this circuit, and from that we derived an expression for the R in. And theoretically, we calculated that R in to be approximately beta plus 1 times RE plus R pi, where R pi is a small signal equivalent base to emitter resistance, which is the ratio of input voltage divided by the input current, that is the VBE over R pi, and RE is your this resistance, and the beta is the DC current gain of the BJT, DC current gain of the BJT. And now we are using the real part here, DC547. This is the general purpose uh, transistor. And essentially we have this load, we have this supply voltage about 5 volt, and we are registering output at this. So we've seen, now I am going to simulate this circuit to compute the R in, which is ratio of voltage divided by the current. So I will apply the test voltage to the input pin of the transistor configured as a CE amplifier. So I will apply the test voltage to the base pin, and then I will compute or calculate the test current IT. Okay. Here IT is essentially my base pin current, that is the IB, right? And IE is going to be the sum of IB plus IC, and IC is going to be beta times IB. So we've seen this from the equivalent model. So refer to the previous model where we have explained the small signal equivalent circuit of this particular circuit, and from that we derive that one. So let us compute R in. So theoretically, we need to know the value of beta, we need to know the value of RE, and we need to know the value of R pi. So VBE is about 0.7, and the IB will be the base current that will flow into the circuit, right? That will give us the value of IB. So we can actually neglect the value of R pi also, and we can say that from this expression, R in is approximately beta times RE. So your inclusion of the resistance RE into the circuit actually improves the resistance, the input resistance of the circuit, right? So beta, it gets multiplied by the factor beta, where beta is usually high. So value of RE is our 10 ohm, assuming the beta is about 100. So we should have the R in about 1000 ohm. But we have used the practical part. So let us see what is the value of the beta here. We have chosen BC547. We'll click here and we'll see what is the value of the beta for this particular transistor. So I am going to find out the beta, if that is written here. So right here, the beta factor is 458.7. So 458 multiplied by the value of RE, that is 10, would be about 4580 will be my input resistance if I calculate that, right? So we can do that, right? So what I need to know, the value of the current and the value of the test voltage. We are interested in computing the input impedance and how it varies over the frequency range. And now I will run the AC analysis and then click OK. If I see the output voltage, obviously, look, this is about 15.5 dB is my gain over the frequency. It is constant up to 100 megahertz. It's constant, but that's not what I want. I want to plot the input impedance Rin, which is the ratio of test voltage divided by the test current IT. So what I'll do, I will add a plot pane. I don't need this signal, so I will delete this pane. Once that is done, I will right click here. I will click add trace. I will find out where is voltage source V of Vt, and is there a source or simply the voltage at the base. That is what I want, right? Let me find out. This is V plus, VB, then I have VE, VO, I of t. Okay, so this is voltage across, voltage at the base actually. Look, all these things got printed there. So I will do it again, add trace, and the voltage at VB is nothing but my test volt and divided by the current that is coming from the same source, I of Vt, and that's my input resistance. Click OK. And this is how this input impedance is varying actually, because I have labeled this, so I'm getting this one. So let us right click here. If I do it linear way, look, theoretically we calculated the Rin to be beta was about 458 multiplied by Re10, so about 408 4,800 ohms, and practically it is like about 7.6, yeah, 7.76K, and this value is constant up to the frequency about 200 kilohertz, and thereafter it drops and drops and drops. And here is how the phase also on the right axis. So you see how to actually compute and simulate the performance of it. So it's quite uh, close to what we calculated. Not really very close, but still approximately, because R pi, we have neglected the contribution of R pi here, right? So if we add the R pi, which is basically VBE divided by IB, VB is our 0.7 and IB is about 8 micron ampere. So that gives you the value of about how much that gives you. You need to calculate that. Let me calculate that if we want to do it accurately. Okay, but I leave it to you. You just take the contribution from the R pi and then compute or simulate the stuff again. Now, how to compute the output resistance? Input resistance we are done. How about output resistance? Output resistance is that I will keep the input side as it is. So it will not be a test voltage. It will be a normal AC input, small signal AC input. And to the output, in fact, I will actually apply the test voltage here to the output pin. That is, this is the ground, and that's my VT test voltage, and because of that the current IT will flow into the circuit, and that is the current actually going right here. Okay, this V signal, if you draw the small signal model, this V plus goes to the ground again, right? Okay. So refer to the previous model, we have referred that. So now how to do that? So what we'll do, we'll add the test voltage, then compute the IT, and R out, which is actually we are looking into the circuit from the output side. R out will be the ratio of VT over IT. Okay, again. And theoretically, in the previous model, we have calculated that R out was approximately, let me recall that, how much was that? The R out expression that we calculated. Let me see that. Okay, so R out was approximately equal to RE, which is this value 10 ohm. So it's pretty low actually. So we'll see now, and this is because of the beta of the transistor. So how we derive this value, if you want to see that, so refer to the previous model that we have created. Okay, so how to simulate that, we'll see. So it is pretty low. You can see that it is just 10 ohm. So this amplifier has a high input impedance, high R in, and low R out. And that's what the property of any ideal voltage amplifier. Input impedance R in is infinity and R out is zero for ideal voltage amplifier. So let us do that, how to simulate it. So what I'm going to do is I will apply the voltage source right here. I will just say this is my voltage source. I will press F6. So this got copied and I place it somewhere here. And then I want to copy the ground or just take it from the schematic editor. I place it here and then I need a wire. So here is the wire that I will connect. Look at this, and that here it goes and here it is. That's it. And we don't need this label now actually. Well, that's not here. Yeah, we just see that. And let's say this is VT1 now. This is VT, so this will be VT1, and the current that will flow is IT1. Okay, and what should be the value of this voltage source, right? So before that, we need to maintain the operating point here, or maybe no need. No need to do that. But we need to maintain the DC bias level here actually. Okay. So before I do that, let us simulate the operating point analysis and see what was the voltage at the output. Okay, so let us press undo, that is F9. So we need to simulate the circuit for the operating point. Click the AC, disable it for a moment, click OK, and then I have output analysis enabled here, the OP analysis actually. So for that, I need to get rid of this AC voltage source also. You don't need AC voltage source here. So click OK. Now this is a purely DC circuit and we'll click OK and see what is the voltage at the VO. That is 4.5857. That's the voltage source we want. That is the DC level at V out, 4.585. So what we'll do is redo the action. So let's say, okay, there is no redo here, shift F9. So is it possible? No, nothing to redo. Okay, so we'll just press F6, click OK, and then let's say place it somewhere here. Then take the ground, place it here, and click OK, then connect the wire here and here. And let's say we are applying a test voltage of 1 volt and divided by the current will be our output resistance. So is that clean and everything good? So we need to click advance. We need to select AC amplitude of 1 volt also. I'm not sure if we want to do the DC value here. So let us not do that because we have a DC level there. And then click there Oh, we don't need to simulate this OP analysis. Rather, we want AC analysis. So I will enable this AC analysis, click OK, simulate, and now VT1. I want actually a VT1. So that is essentially a VO. Oh, so let us add trace, that is VO divided by I of VT1. That is my current. The green curve is deleted, to be deleted. And what is the output resistance? Look here. So I will right click here. I will click linear, and it's 8 ohm, which we theoretically predicted. Look, R out is RE, and RE is 10 ohm in our circuit, and this is exactly a good match with this value of the experiment that we have done. So very good. So we applied the test voltage, and we take the ratio of test voltage divided by a test current. Okay, here also we could have applied the test voltage of 1 volt and then simulate what you want. We can do that actually. So let us try to do that. Let's say I apply a 1 volt here, and but then you need to use the AC voltage source here, right? Let us say the AC amplitude. Okay, and you don't need AC here, right? You just leave it like that, or just disconnect, or keep it 0 actually, because you don't have any circuit there. Okay, so this is, let's say 0. You don't have a source there, and now of course your output impedance is 0. And now you can actually address and say VB divided by the current flowing through the VT, due to VT. And look at this, 2.81 ohm. Oh, 2.18 is very small. So here's the wrong thing. Why? Because we have changed the DC bias level. The transistor is not in an active mode. The earlier DC bias was properly set with the voltage of 0.7 volt. Is that so? Let us do it again, save it and run the simulation. And now we see we have about 20 ohms. Still, it is a problem. And that problem is because we have a voltage here applied to the output, and that is causing a problem. You need to actually disconnect this and then right click this, go back to DC level of 1 volt, and then simulate. And now look at this. This is 3.6K ohms, which is what we theoretically calculated. Theoretically, we calculated 4.6 ohms, and this is now this one. Very good. What about with the DC bias level of 0.7, earlier voltage bias level 0.7? In fact, so if that is so, let us do it again. And it's about a little bit more, right? It's almost double, but still it's in the same order. It is in the same order. Like theoretically, we have like close to 5K, and the practically is 7.7K. So this is how we explain to you how to compute and calculate the input impedance and the output impedance of the circuit. This is applicable to any circuit that you will do. Okay. So stay tuned for more informative videos like this. And till then, wish you happy learning. Share it with others for a wider reach. And like and subscribe to the channel if you are new. And that's it. So we've got this one. Very good. Okay, bye-bye.